Hello everyone. Welcome to the Thanksgiving lecture, I guess. Today we're going to talk about just a few more topics on frequency response, and then we're going to get to more topics on frequency response when we get to feedback. But for now, we're still just talking about poles and zeros, so just some final points on that today. So to remind you, the way we found our poles so far, since we have really only talked about poles, and that's because we talked about transistors and how when you simplify them down, what they end up looking like is a current source into a resistor and a parallel and a capacitor in parallel, and a resistor and a capacitor in parallel with a current source into them looks like a low-pass filter. So just to remind you, what we've done so far is we've sat on a node and we've looked around and seen what capacitance we see on that node, and then we've found the R on that node, and that's just the small signal impedance, and that was our R and our C. We took 1 over RC, which is the radians where there's a corner frequency on a Bode plot. When we looked at our MOSFET, we found a whole bunch of capacitances. These are the total possible capacitances, and we don't see all of these when we are in the active region. For example, the gate bulk capacitance, that does not exist because what happens is you get a layer of charge in the channel, and that charge is actually, if you look in books or on the slides, that's considered gate source capacitance. So the gate bulk, because the gate is coupling to the charge in the channel, it doesn't see the gate bulk, and this capacitance goes away. And when we talked about BJT, we talked about every place that there's a PN junction, you see a capacitance. There's two types of capacitance. There's the junction capacitance and there's diffusion capacitance. Diffusion capacitance, again, is a reverse bias PN junction, and junction capacitance is forward bias PN junction. The junction capacitance it doesn't look like the capacitors that you've seen in circuits in your previous circuits classes. It's not two plates that need to charge and discharge when the voltage across them changes. It is related to how long it takes charge to redistribute itself when a voltage changes across a PN junction. So the mechanism's the same. You change a voltage and some charge has to move around, and it takes some time. So this is another a capacitive behavior. It gives a capacitive behavior, but it doesn't look like a parallel plate capacitor. Whereas the diffusion capacitance, that looks more like your parallel plate model. Okay, and then if you draw those in on the small signal model, you've got your base to emitter, base to collector, and collector to substrate. Okay, and we actually didn't go through the math in class, but I just want you to realize that the size of these capacitances is on the order of picofarads. Okay, and just on Friday we had a few of you show up, but quite a few of you were feeling the pain of the week, so you weren't there. But we talked about this particular circuit, which is a common emitter followed by an emitter follower, and we did evaluations of capacitances at different nodes. And though there are 3 nodes moving, V in, V n, and V out, we just looked at V in and V n. Okay, so let's do that real quick. We have 2 capacitances from the base right here. We have one to the emitter and one to the collector. The capacitance that goes from the base to the emitter, you can see that the emitter is grounded here. So in that case, if you're sitting on the input and you look at that capacitor, the far side is connected to ground, and when you move, the capacitance you see is exactly the capacitance that you've calculated for this capacitor. So if the far side of the capacitor is connected to ground, you just use exactly the value that you've calculated for that capacitor. The value for the base collector is a little bit different, because when you move Vn moves an awful lot. Okay, if there's a bigger voltage change across the capacitor, that means more charge needs to be put onto that capacitor to accommodate that change in voltage across it. And if more charge is being pulled off of the input, that capacitor looks quite a bit larger than the capacitor that you've actually calculated for that junction. And how much bigger? Well, the output moves up by AV, and let's say you move V in by delta V. The input moves delta V in one direction, the output moves AV delta V in the other direction. So we have a net change of voltage across there of that delta V times 1 plus the absolute value of AV. And since that, even though V in is just moving delta V, the actual capacitance right there is perceived as whatever the capacitance that you calculated times 1 plus AV. And that's the Miller effect. If you have trouble with that, come to office hours and all, so until you feel comfortable with it. So when you write an equation for the capacitance that you see at the node here, you have CBE plus CBC times the quantity 1 plus absolute value of AV. Okay, so that's an example of a capacitor that you calculate the value of, but when you actually use it in the circuit, you have to change its value to recognize that the voltage change across it isn't, that the far side isn't connected to ground. Okay, so that's Vn, just has those two capacitances. Vn has a whole bunch of capacitors connected to it. It has the collector base for Vn, the collector substrate for Q1, I'm sorry, and then for Q2, again, it has the collector substrate and the collector base, and then for Q3, it has the base emitter and the base collector. Okay. Turns out that a number of those are connected to AC grounds, to virtual grounds. And remember, if the other side of the capacitor is disconnected to ground, whatever value you calculated for that capacitor, that's what you can use in your equation. So if you look at this, the base collector for Q3, that's the far side of that capacitor is connected to ground, since the collector is connected to ground. So that one you just use as its value. Substrates are connected to a DC value. So anything connected to the substrate, you can assume that the other side is to a virtual ground. This is a biasing node. This wire right here is set by this biasing circuitry, and it's a DC value. Okay, DC value is a virtual ground when we're in the AC realm. Okay, so the far side of the CB of Q2, the far side of this capacitor is also considered connected to ground. So all of these, you just use the value that you calculated for them, and you're done. Okay, what's left is the CCB of Q1 and the CBE of Q3. So the CBE of Q3 and the CCB of Q1. Let's look at those. The CCB of Q1. Remember when we were over here and we looked at this capacitor, we had to multiply that by 1 plus AV. But now you're on the other side of that amplifier, and you need to figure out what capacitance you're seeing there. Now remember, if you change V in a little bit, your output changes by AV times that change in voltage. Going back the other way, if Vn changes delta V, that means that Vin changes delta V over AV. In other words, it doesn't change very much at all. And as another simplification you can use, because Vn is only moving delta V over AV,